So a little bit about me. I'm a research scientist here, and previously I was a research scientist in a variety of industry and research labs, working on a wide variety of AI and machine learning topics. And more recently, before RealityEngines, I was working on artificial intelligence and ethics, which is sort of partly relevant to the topic that we are going to talk about today. And I thought I would start this talk with this very scientific graph that shows that fairness and bias, or research in fairness and bias in machine learning has been increasing over the last few years or so. And even though it's sort of humorous, this is actually true. And because when I was working in ethics in sort of 2014, and when I told my friends that I was working in machine learning or AI and ethics, I used to get very weird looks from my friends. I still get weird looks though, because I'm working in machine learning. But more seriously, why are we interested in explainability and bias right now? So in the last decade or so, there has been a lot of a significant rise in machine learning and AI models that are deployed in applications that have a significant impact on human life. And moreover, most of these, even the best of these models are more or less black boxes even to the experts that develop these models. And even worse, some of these models end up learning human biases and end up acting unfair to large groups of people. So one particular application that has gained a lot of attention in the media over the last few years is the COMPAS tool, which is a tool used by courts to decide whether a defendant undergoing trial should be granted bail or not. For example, if you look at this particular instance, you have this white person that is given a score of 3, which is supposed to be a lowest score that this person will reaffirm. And this black female is given a high score of 8. So without much more information about these two persons, we might not know whether these scores are reasonable. But if you look at the background information for these two persons, you will see that this white person has a number of prior offenses. For example, he committed 2 armed robberies. And this black person didn't have any significant prior offenses. And in fact, this black person didn't commit any further offenses, but this white person ended up committing a significant future offense. So this was uncovered by this organization called ProPublica, and they found out that if you're non-recidivating black people are twice as likely as non-recidivating white people to be labeled as high risk for this tool. So this tool sort of shows why we need explanations from a model, and why we also need to make sure that our models don't have any bias. So we need tools and techniques for not just explanations, but also for detecting and removing bias in our models. And specifically about explainability, it's not just useful for laypersons that might be interacting with these models. For example, if you're an AI developer or practitioner, you might also benefit by having access to explanations in order to quickly iterate and debug your model. So that's another use case for explanations. And in certain domains, there might also be a legal need for explanation. For example, if you're a bank and if you're building a model for deciding on loan applications, then you might be required by law to provide explanations when you reject somebody's loan. And this is another strong case for having explanations built into your model. So what is explainability and how do we get it? So one easy way to get explainability is by starting with a model that is already explainable or interpretable. For example, in the COMPAS domain, you could train a decision tree. And the decision tree for the COMPAS domain or application could look at something like this. It might look at the number of prior offenses that a person has, and if it's 0, then the decision tree might label that person as low risk. It's a line upwards so that you get more explainability for the same performance. And in the last 3 or 4 years, a particular class of methods known as feature attribution methods have gained a lot of adoption in both the industry and academia. So what they do is they take any arbitrary classifier and they don't look at the internals of the classifier. They just treat the classifier as a black box. So you're not worried about the internals. And what they do is instead of explaining the classifier as a whole, they look at how the classifier handles one particular input. And what the explainer does is it takes in the input, it takes in the classifier, and it takes in the output, and it spits out an explanation in the form of feature weights. So that's why the name feature attribution methods come. And the weights sort of give you a good idea of which features were important for this particular prediction. And another important thing is most of these methods they work with what are known as interpretable instances rather than raw features that most machine learning models use. And so what is an interpretable instance? So the idea is that it's very difficult for laypersons to understand raw feature spaces that a lot of modern machine learning systems use. For example, if you're building a text classification system, you might be using word embeddings, but you can't throw a word embedding at somebody and expect them to understand what it means. And the idea is that humans are much better at understanding presence or absence of certain things, components. And what we do is we, given any input that we want to explain, we convert the input into a new binary feature space, and we call the new input an interpretable instance. So what does it look like? So for example, for text, an interpretable instance will be a binary vector indicating the presence or absence of certain words in the text. And for images, an interpretable instance might be a binary vector indicating presence or absence of pixels or contiguous regions of the image. So with that background, we come to the first explainability method that gained a lot of popularity. So this is LIME, which stands for Locally Interpretable Model Agnostic Explanations. And it was introduced in 2016. And it's a very neat idea, and it's one of those ideas that when you understand it and get it, you sort of kick yourself for not getting it in the first place. So how does LIME work? So LIME takes any classifier, it takes any arbitrary classifier, and the classifier can be very complex, such as this classifier that we've shown here. And it takes an input instance that you want to explain. For example, this particular line shown in blue. And what it does is it sort of samples around the instance that you want to explain. It draws other inputs from your input space. And it converts them into binary vectors that are interpretable, ones and zeros. And what it does is with these new set of data points, it fits an interpretable model. And in this particular case, the interpretable model that we are looking at is a linear model. And once you have a linear model like this, you can use the weights of the linear model to sort of directly assign feature importances. So in this case, we have, for example, we have a weight of 1.1 for the first feature or the second feature that says this feature is sort of important, and probably this feature with weight 5.6 is the most important feature for this particular instance and classifier. And you can sort of play around with this basic model. You can enforce parsing constraints on the linear model and get a feature importance for only the top features. So here is one example that you might have. Let's say you are building a text sentiment classification system, and one particular input that you are dealing with is the movie is not bad. And if you apply LIME to this, you would probably get 0 scores for words that are not relevant in your input. This movie is. And if the overall score for this particular input is positive, indicating the emotion is positive, you might have not being given a high positive value and not being given a slightly negative value. So that when you sum up these values, you get an overall positive value. And how does LIME work for images? We look at binary vectors that are contiguous regions in the image. In this particular case, a classifier output a label cat for this image. And LIME's explanation is that this particular region highlighted in green, which is a cat, contributed highly to the classifier's output. And the region shown in red, which is a dog, contributed towards moving the label away from cat. And you can also apply LIME to classify multi-label classifiers. In this case, if you have your classifier output multiple labels such as electric guitar, acoustic guitar, or Labrador, then you can see that LIME will faithfully pick out regions in your input that correspond to the different labels. So LIME is not only useful for explanations. You can also use LIME for debugging classifiers when you're developing classifiers. Let's say you have an image classifier, and I classified this this image of a husky as wolf, as a wolf. And you might think that this is a reasonable mistake to make, given that huskies look very much like wolves. But if you look at what LIME produces as an explanation for this classifier, on this instance, you would see that the classifier thought that the background snow was very important in classifying this image as a wolf. So this is really not a good thing to happen. So what happened was the classifier didn't use any relevant features. It was relying on background features to label this image as a wolf. So you would do that. If you get something like this, you would then do some more feature engineering or some more model engineering to improve your model. You can do a similar thing for text. One example is, let's say you have a text classifier that's trained to classify emails into multiple classes. And in this particular case, you have this email classified as belonging to atheism class. And if you look at the words that the classifier thought were important for this classification, you see that the classifier used words and tokens from the header of the email. For example, it used the domain name and it used the university name in the footer. So ideally, the classifier shouldn't be relying on information in the header and footer to get this label. So if you see something like this, then you can hopefully remove that irrelevant information from your inputs and then improve your classifier. So that's the first method, and there's another recent method called SHAP for feature explanations. And one neat thing about SHAP is around the time that LIME was introduced, there were many other similar feature attribution methods such as integrated gradients, Shapley values, and deep lift. So LIME is this neat method that sort of integrates all these different feature attribution methods into one nice theoretical framework. So what happens is all these other methods, they become special cases of LIME. So they become special cases of SHAP, sorry. So what is SHAP? So SHAP derives from game theoretic foundations, and it comes from Shapley values that are used in game theory to assign values to players in cooperative games. So what does it mean? Let's say you have a set S of n players participating in a game with payoffs defined for any subset S of players participating in the game. And it's given by this function V of S. And what Shapley values provide is they provide one fair way of dividing up the total payoff among the n players. So you look at the total payoff that your whole set will get, and Shapley values are one nice way of dividing up the payoffs among the players. And the definition is quite intuitive. So let's say you are interested in the Shapley value for player I. And what you would do is you would look at a particular group that doesn't contain player I. And you compute the payoff for a group that doesn't have player I. And what you do is you then compute the same payoff with the player included in the group. And then you compute the difference. And then you repeat this over all possible groups. And you take average, and that will give you the Shapley values for player I. It's quite neat. And so what are SHAP explanations? And how do they tie in the players and games? So the idea is that players are features, and the payoff is your model's real value prediction on a particular instance. So with this, you can easily see how Shapley values can be used for feature explanations. And the authors have a very nice and well-documented implementation for SHAP values that you can get here. And you can find explainers for different kinds of models. You can find explainers that are very fast and exact for tree-based classifiers, and you can find approximate explainers for black box models and deep networks. So it's a quite nifty toolkit. So here's an example of SHAP applied to a an input that comes from the UCA and the data set. So the goal of this data set is to classify whether a person is making about $50,000 given certain features such as their gender, whether they made any capital gains in the last year, and their relationship status, and so on and so forth. So in this case, the classifier's output is 0.16. And we see that the base value for the classifier is 0.248. So these are probabilities that the person is making about $50,000. So in this particular case, the classifier thinks that this person has a lower probability of making about $50,000 than the average in the training set. And so how do we interpret this? So you can think of these blue and red bars as moving the classifier's output from the base value towards actual output value. So all the red bars, they move the output value higher, and all the blue bars, they move the output value lower. So let's say you have a base value that is located somewhere here, and you have a feature, that feature 41 with a certain importance. So what it does is it moves the base value slightly lower. And then you have another feature F3, that has another particular feature importance that will again move the base value lower. And these are all negative values, so that's why they move the base value lower, the output lower. And you have another feature that has an even higher negative score that moves the output even more lower. And then you have feature 34 with a slightly positive score that moves the output slightly higher. And then you have feature 87 that has a slightly larger positive value, which moves it even more further up. So the idea is that you can explain the difference between the base value and the output value of the classifier using the lengths of these green and of these blue and red bars. So here's another input explained by SHAP. In this case, the classifier thinks that this person is very highly likely to have an income of over $50,000. So the idea is that the feature reprocess information that you need to change a specific condition to a designated value. Once again, if you're a bank and if you're a billing model for deciding on loan applications, then it will be very helpful to provide to loan applicants, if they get rejected, what they will need to change for their loan application to get approved in the future. So explanations alone don't give you that information to change predictions. And there are also some issues with SHAP and LIME. So one big issue is that SHAP and LIME sort of work more or less fine if you are dealing with linear models. So the idea is that if you have trained a linear classifier like in this case, and if you look at SHAP values and LIME values across your input space, they are more or less constant and stable. But if you do the same for a highly nonlinear classifier, you can see within very small regions, your SHAP values and LIME values, they flip around a lot. So even though the explanations are nice, they tend to be sort of highly variable for instances that are similar. So why is that an issue? It's an issue because they don't provide you with much insight into how the model will behave on new instances. Let's say that you don't know anything about English, and let's say you are given this input, and you are given information that the classifier had a positive score for this input. The movie is not bad. And you are given the LIME explanation for this input. And the LIME explanation says that the classifier thought that the word not was very important in moving the output to a positive value. And it should be reasonable to assume that given similar instances, this feature should behave in a similar manner. And you should also be able to assume that the classifier should also behave in instances that are similar. But if you look at another instance that is very close to the original instance, the movie is not very good, then you can see that the explanations for all the different components will flip around. So you have the explainer saying that the word not was highly instrumental in driving down the prediction as opposed to driving up the prediction in the first case. So the key idea is that it's very hard to understand how the model will behave on the instances. So people have come up with, the original authors of LIME have come up with a new form of explanations called anchors. And anchors are rules that have satisfied will sort of anchor your prediction to a certain value. For example, an anchor in this case would be the rule that says if not and bad are in your input instance, then your output will be positive. As long as this rule is satisfied, the output will be positive. Very high likelihood. But if this rule is not satisfied, then the rule won't say what will happen with your output. And similarly, another anchor for this input will be that if not and good are in your input, then it's highly likely that you get a negative value from your classifier. So there's still research going on in building better explanations that are more robust and more useful. So the key take home message I would say is that explainability is definitely possible and need not come at the cost of performance. But on the other hand, explainability is not enough. You still need things such as recurse when you're building models that make a lot of important decisions. So that covers the explainability part of the talk. And I think we move on to bias. And if there are no questions, I'll just
So I feel like SHAP and LIME, and I say this thinking that most people in the audience are probably practitioners and not academics. SHAP and LIME are pretty decent on NLP and image problems, but they totally fail on tabular kinds of things. I don't know if y'all have worked on anything similar and have different insights.
So what would be?
Any kind of structured data, I found that SHAP and LIME just really, frankly, perform very poorly. So like you just showed, the SHAP values are extremely likely to flip on either side of the decision boundary on very, very similar cases, regardless of how your model actually
Definitely.
did that.
I mean, it's still we still need a lot more research to be done in this space, and I think that also goes for text-based and image-based models. I don't know if you have any of that.
Also, I just like
Yeah, just-
I like that as a term.
Got it.
I have another quick question here. So it's coming from abyss of ignorance. Coming back to LIME, it sounds like you're trying to explain a very highly nonlinear model with a linear approximation. Like, isn't that incredibly sensitive, and isn't it a little disingenuous for the field to call it an explanation? It sounds more like an interpretation that's super unstable.
Yeah, definitely. That's one of the things that I mentioned in my slides. It's highly stable. It's highly unstable when you're dealing with nonlinear models, and that's why we need new forms of explanations that people are still working on that are not so well developed as LIME. So LIME and SHAP are used a lot by.
So what do you say is actually useful? I mean, in the sense that it's so unstable, right? I mean, it's a.
I mean, we don't have anything better so far, so we are working on it and we'll have something better.
Are y'all using any of this stuff in production?
Sorry?
Are y'all using any of this stuff in production? I say that as somebody who works in a healthcare company and like deeply values any responsibilities that do with doctors on a regular basis, but we've just, it utterly fails for us.
Yeah, I saw
Similar
that.
experience?
Yeah.
Yeah. It sucks.
Yeah. But there's nothing better so far.
Clients don't appreciate that.
I think I mean, if it's a simple question, we can take otherwise.
For the NLP example that you provided, that I guess a failure case, like it seemed to me that this failure case was founded because that SHAP was assuming that the features acted independently, I guess.
Yeah, that's another big assumption.
Yeah. So that correlations between features.
That's a good point. Right. So on to bias. So what exactly is bias? So bias in this context is unfairness or the absence of fairness, more or less. And we should keep in mind that the bias that we are talking about in this case is much different from the standard statistical bias in machine learning that we are all used to. And this is the bias in the bias variance trade-off. So just a small note on that point. And so do we have any good definitions of fairness or bias? Unfortunately, there are many definitions of fairness and bias, and most of these definitions are application dependent. And I would say no one definition is better than the other. And there's a very good tutorial talk titled 21 Definitions of Fairness by Naveen at ACM FADSTAR 2018 last year. But he goes through multiple definitions of fairness. And the key point in his talk is that there are not just 21 definitions of fairness, but there are in fact dozens of definitions and not just 21. So what is fairness generally? So the idea is that we have different groups of people that are split by one or more attributes, and ideally we would want our machine learning models to treat all these people, all these different groups of people in the same manner. And this is what all these different definitions strive towards. And we'll go through some of these definitions now. And the basic setting that we are working with is that we are dealing with a classifier C, which has binary output labeled positive and negative, and a real value score S. And the classifier is working with instances or data points that are generally humans or groups of humans. We are not interested in fairness or bias for example, handwritten digits. And generally the positive class is desired, assumed to be desired, and the negative class is assumed to be not desired. And we have inputs X, and within the input we have one or more sensitive or protected attributes G. The attributes can be something like gender or race, and these attributes can have multiple possible values. And we generally call a set of instances sharing a sensitive attribute as privileged if those instances receive more positive labels, and we call the other instances, other set of instances unprivileged, and they generally receive less positive labels. And we have the true output Y. So with that setting in place, one very simple form of fairness that you can try is a fairness through blindness or unawareness. It's a very simple idea. So the idea is that we don't consider any sensitive attributes such as race or gender when we are building a model. It's a very neat idea, it's a very simple idea, but it doesn't work. So one big advantage of this definition is that it seems to have some support in the law. For example, there is this legal concept known as disparate treatment that seems to sort of align with this definition. But unfortunately, your other attributes might be correlated with your sensitive attributes. For example, if you're dealing with race, then you might find out that things like geographical location are correlated with race. So by just removing sensitive attributes, you can't make sure that your model is fair and free from bias. So you can sort of improve upon this by using what is known as the statistical parity difference. And the idea is that different groups of people, when you partition them based on their attributes, for example, males and females, they should receive the same proportion of positive and negative labels. And ideally, that means making this value as close to 0 as possible. So it has some good points in that this also seems to have some support in the law through a concept known as the 4/5 rule. And this might also remove historical bias that is present across different groups. But it also has disadvantages. One big disadvantage is that this definition is satisfied by a lot of trivial classifiers. For example, if you have a classifier that just spits out the same proportion of labels across different groups randomly, then it will satisfy this definition. And if you have a classifier that assigns all positive labels or all negative labels for all instances, that will also satisfy this definition. Another bigger problem with this definition is that if your ground truth rate prevalences across groups are different, then this definition rules out a perfect classifier from being used. So to rectify this, you can use something known as the equal opportunity difference. So what it does is, instead of just looking at groups as a whole, you look at the number of people in your group that actually have positive labels, and you say that given a certain group has positive labels, you look at the fraction of those instances that are labeled positive by a classifier, and then you say this should be the same across all groups. And this, once again, has some advantages. The biggest advantage is that it allows you to use a perfect classifier, unlike the previous definition. But unfortunately, it also tends to perpetuate historical biases. For example, if you're building a hiring model, and if you have 100 people from a privileged group and 100 people from an unprivileged group, and let's say there are 50 qualified applications in the privileged group and just 4 in the unprivileged group, you can satisfy this definition by just hiring 25 from the privileged group and 2 people from the unprivileged group. And things like jobs, they tend to perpetuate across generations, and that's why we say that this definition perpetuates historical biases. And more importantly, related to the first example that we saw, if your application is punitive in nature, then you might stipulate that your false negative scores across different groups should be the same. For example, if you're dealing with a COMPAS tool, you can say something like this. You can say that you can stipulate that the proportion of black defendants who don't receive it and receive higher scores should be the same as the proportion of white defendants who don't receive it and receive higher scores. And this was in fact what ProPublica uncovered. So in their article that got a lot of attention in the research community, they found out that this wasn't satisfied by the COMPAS application. So that's 4 definitions stand. And we still have 30 more to go. That it's impossible for both these definitions of fairness to hold. And when your prevalence rates are different. And this is just one possibility research, but there are some more research that show in general it's very hard to have more than 3 definitions to hold unless certain other conditions are satisfied. So that's it with definitions. So let's say you use one of those definitions and find bias in your model. So the question that you can ask then is, can you do something about this bias? You can definitely do something, and this is called mitigation or bias mitigation. And there are algorithms and tools that have been developed in the last few years that remove or decrease bias. And this can happen in 3 different places. So you can do bias mitigation before your model is built, or you can do it when your model is being built, or you can do it after your model is built with the predictions. And one tool in particular has a lot of these measures and algorithms implemented. That is the AI Fairness 360 tool from IBM. And I'll walk through some examples from this toolkit. So if you look at the COMPAS example once again, and if you build a simple classifier with a dataset, you can then measure statistical parity difference and equal opportunity difference. So any values that deviate significantly from 0 are indicative of bias in your model. And what it shows here is that there is significant bias when you use these 2 scores for bias. And we can put this model through, we can put this pipeline through bias mitigation algorithm. So one algorithm is known as reweighing. What it does is it increases weights for your instances so that unprivileged instances with positive labels get higher weights and privileged with negative labels get higher weights. And similarly, it decreases weights for unprivileged instances with negative labels and privileged instances with positive labels. It's a very simple idea, and it seems to work surprisingly well in practice. And what happens is when you put this, when you apply this to the COMPAS data set, you can see that it reduces bias significantly, at least when you use these 2 measures. And it doesn't impact accuracy that much. And there's another mitigation algorithm for applying when the model is being built. So what it does is that's an adversary that tries to predict the value of a sensitive attribute from the output. And your model is trained to reduce the adversary's performance. Thank you.
Getting played off.
Well, it's almost time.
Yeah, that's good. Just one more thing. So what happens when you apply this model? So this model also works, it reduces these 2 forms of bias. And it happens to slightly increase accuracy in this case, which might not be that significant. And the final bias mitigation algorithm is known as reject option classification. It's also a very simple method. What it does is, if your classifier score is a probability score, and what it does is if your output is within a small band around 0.5, it makes the prediction positive if the instance is unprivileged, and if the instance is privileged, it predicts negative. And at least for the COMPAS data set, this seems to work, this mitigation algorithm. But for this particular case, the accuracy gets reduced a little bit. So I guess that's about bias measures and mitigation algorithms. And the take-home message here is that there are many different forms of bias and fairness, and it's still an ongoing research area. And thankfully, some forms of bias can be decreased with algorithm, usually with some loss in performance, but if you're happy, that needn't be the case. I think that covers it up. And hopefully after mitigation, things can be well done. Everybody's treated the same.